In this video, we're going to talk about sets of numbers and number lines. There are many different sets of numbers that we talk about in mathematics. For instance, we can talk about natural numbers, which are numbers, positive integers, basically the numbers that you teach someone to use when they're learning how to count for the first time. Now, if we add a 0 to that set of numbers, we have what's called the whole numbers. Eventually, mathematicians realized that we can have negative numbers too, and so they added negative numbers to the whole numbers, and we had integers. And then eventually they realized that sometimes we have fractions, which leads us to rational numbers. A rational number is any number that can be expressed as a ratio of two integers. And essentially that means all numbers that can be expressed as a decimal with a definite end. So examples would include 74.3, it ends, or negative 2.9196508, it ends. However, there are other numbers that don't end but are expressible as a repeating decimal. So for instance, the number 3.222 with a repeating decimal, or negative 15.262626 with a repeating decimal on the 26. Those would be examples of rational numbers, which leads us to believe that there will also be irrational numbers. And irrational numbers include any real number that can't be expressed as a decimal with a definite end, and that's also non-repeating. The most famous of those numbers is pi. Pi is equal to 3.14159.265, etc. Another example is the square root of 2. The square root of 2 is an infinitely long decimal that does not ever repeat, and there are countless others. Now, if you take rational numbers and irrational numbers and put them together, you get real numbers. And it's likely that any number you've ever considered before has been a real number. There are number systems that expand beyond real number systems, such as the complex number system, include numbers that aren't real, but we're not going to be dealing with those in this course, or if we do, it'll be very brief. Now, we want to learn how to discuss things in set notation, so we're going to be describing sets of numbers in this slideshow, and we're going to have to learn the appropriate symbols. If you see a brace bracket and then some writing followed by another brace bracket, what this means is the set of. If you see the symbol E, looks like that, but it's rounded, that means is an element of. And if you see this slash like that, it means such that in this context. So let's describe the following in set notation. When we see this arrow on the end here, what that means is that we're going to keep on shading in the numbers forever and ever. Now, I want you to think that what we're going to try and do here is write out the set of every single number that's being shaded in. So for instance, the number 1 is shaded in. The number 2 is shaded in. But so are the decimals in between. The number 2.5 is shaded in. Pi, 3.14159.265, etc., that's right about there. That's also shaded in. Somehow we have to be able to list all of those numbers. And so what we're going to do is we're going to use the following procedure. We see that the shaded part of the number line refers to all the numbers to the right of -2. And on a number line, numbers to the right of a given number are greater than. So on first glance, we're going to say that our condition is x greater than -2. We've shaded in all the numbers greater than -2. And that's a good start. But we also have to realize that this at -2 itself, that value itself is shaded in. So we have to include -2. So that means we're going to think x is greater than or equal to -2. Okay, but we also have to somehow indicate that we want to only be talking about real numbers, not unreal numbers or imaginary numbers. And also we want to indicate that we're not just talking about integers. We want to indicate somehow we're talking about numbers greater than or equal to -2 that are real. And the way we write that mathematically is what this question is all about. So, like it says in the last sentence on your screen, this is a real number line, which means we're referring to all real numbers greater than or equal to -2. And the way we write that is as you see here. We write the set of, which is given by these two brackets in unison. We say any x that's an element of the real number system, in other words, any x that is a real number, such that that value of x is greater than or equal to -2. When we write this out like that, what we've done is effectively described the shaded in number line that you see at the top of your screen. Numbers that are shaded in will be referred to as x, and they will all be elements of the set of real numbers. We've got such that and x greater than or equal to -2. And so the way that reads is the set of all values that we will refer to as x that are elements of the set of real numbers such that x is greater than or equal to -2. A little more casually, we'll say the set of all real numbers greater than or equal to -2. Now, when referring to a set of numbers that contains an infinite number of values, it's quite common to follow the format that you saw on the previous slide. The set of, and then we say x will be a real number such that, and then we'll indicate some algebraic condition on x. So in the question that we just answered, the algebraic condition on x was x greater than or equal to -2. Now we do that because there's an infinite number of values that are shaded in, so you can't simply list all of them. As we'll see, however, we don't always use this form, especially when it's possible to list every value shaded in. And that's true in the next example. So just to show you what I mean, this example that we just did, it's impossible to list them all. There's infinite numbers of numbers. There's decimals. There's no way I could just write them all with and put commas in between. It would be impossible. But sometimes it is possible. For instance, this question right here. We're literally just talking about 5 values there. So in our solution, we want to express in set notation a set containing the numbers -3, -2, -1, 0, and 1. And the answer is literally as simple as writing the set of -3, -2, -1, 0, and 1. Because we can list every number, we don't have to refer to x as an element of the reals or any other mathematical qualifiers. We just list the numbers. However, if you want to, you could be a little bit more clever. I'll show you what I mean. Sometimes someone who's being pretty clever will say, well, any x that's an integer such that x is somewhere in between -3 and 1 inclusive. By writing this at the start, they're telling us that the only numbers we'll be considering are integers, and by writing this, they're telling us that the number will be somewhere in between -3 and 1 inclusive. We'll talk a little bit more about this format right here. But for purposes of this video, we're going to say you don't actually have to do it that way. You can simply just list the numbers the way you see at the bottom of the screen. So it's totally sufficient. When there's a finite set of numbers, you can just list them. Okay, and this is an explanation of what we said a minute ago. You could do it a little bit more sophisticatedly. Now, it would be wrong to write x is an element of the reals such that -3 less than or equal to x less than or equal to -1. Why is that? Well, it would be wrong because we would be leaving out it would be wrong because if we wrote x as an element of the reals, we would be including, for instance, the number -2.5. or the number 0.2. These numbers that I've indicated in red satisfy this condition, but they're clearly not shaded in. We don't want to include them. So to write what you see here that I've circled in red would actually be incorrect. Now, for the remainder of this presentation, though, we're going to deal with intervals of numbers that contain an infinite number of values and require a statement of the form shown. This is the most common way of writing out answers in set notation in this course. So suppose we wanted you to tell us what are all the values that we've shaded in here. This arrow here indicates that we're going infinitely far to the left. Since we have an infinite number of values, we obviously want to say x is an element of the reals such that, and we want to close our brace brackets because together the first and last bracket mean the set of. And we're including values that are less than -1. We're not actually including -1 because there's an empty circle there. So we're just going to say x less than -1, and what you see in red is the final answer. So like we say typed out, we're referring to all real numbers less than -1. Because there's an open circle at -1, we know we're not including that value in the set, so therefore we can state the set of all x element of the reals such that x is less than -1. Now, what if we have something like this? Well, we've got an interval infinitely far to the left and another one infinitely far to the right. So because there's two different intervals, we're going to write it out as two different intervals with a comma in between. The first one is all numbers less than -3 to the left of -3. And we're also including -3, so we'll say less than or equal to -3. We're including -3 because of that shaded in circle. Then on the right, we're saying all numbers greater than 4, but we're not actually including 4. Because it's an open circle. So we say all numbers to the left of -3 including -3, all numbers to the right of 4 not including 4, and there's our final answer. Okay, so like it says here, we have two different intervals to consider. One of them refers to all numbers less than or equal to -3, and one of them refers to all numbers greater than 4, and we write our answer like that. Now, this gets a little bit tricky. This next question. We want to include an infinite number of numbers. The reason I say it's an infinite number of numbers, if that's not clear yet, is we're not just including the numbers 2, 3, 4, and 5. We're also including all the infinite number of values in between, all the real numbers that are decimals in between. We can't list them, so we have to have a method, and that's what we're doing here, x element of the reals such that. Now, I'll show you the most common wrong answer. People sometimes will write x greater than 1, and then they'll write x less than or equal to 5. Just for a minute, ignore that. I put a negative there at the start by accident. But what you see here makes sense. Someone who would write that answer knows what they're doing, but there is a mistake. And the reason there's a mistake is if you tell me x is greater than 1 in this context, that tells me that you're including every number to the right of 1. And then if you tell me x is less than or equal to 5, that tells me you're including every number to the left of 5. Well, put those together, you've just shaded in the entire number line, but that's not what you wanted to do. You didn't want to shade in the whole thing. So instead, if you only want to show me the so what we've said here is this would be the wrong answer. That's incorrect for the reason I just mentioned. If you want to show that we're only including numbers in between 1 and 5, the way to do that is to write the smaller number less than x less than the bigger number. And what we've just done is we've written one condition that includes two different parts to it. And so we're saying 1 has to be less than x, which has to in turn also be less than 5. Now, we're not going to include 1 because there's a empty circle at 1, but we are going to include 5 because there's a closed circle there. Now, just to show you why this is true, imagine, I want to take a brief moment and show you why that works. Imagine any number that's shaded in, any number at all. I'm just going to choose the number 4. If this right here, 1 less than x less than or equal to 5, is an accurate descriptor of the shaded region, then you should be able to put the number 4 in for x and come up with a true statement. Well, is it true that 1 is less than 4 while at the same time 4 is less than or equal to 5? Yes, both of those statements are simultaneously true. But to show you that a number out here would make it false, let's try putting any number out here, any number with that's not shaded in, let's try putting that in this little qualifier and see what happens. So let's say we choose the number -3. If I say 1 is less than -3 is less than or equal to 5, right away I have an incorrect statement. That means this whole thing's not true. That means that -3 is not included in this algebraic thing, which is good because we didn't want -3 to be included because it's not shaded in. And also, if you picked a number out here, let's say we picked a number like 7, if you plug that in for the x, it would say 1 less than 7 less than or equal to 5. 1 less than 7 is correct, but 7 less than or equal to 5 is incorrect. So that would be wrong, which is good for us. We wanted it to be wrong because it's not shaded in. So to summarize, did a lot of talking there the last minute, but to summarize, basically the way to do it when you have an interval in between two set numbers, write the smaller number less than x less than bigger number, and then you can decide whether or not to put equals on either of your less thans, possibly both of them, and in this case you're going to put it just on the one near the 5. Okay, so this is the descriptor typed out of why we do this. When we have an interval sandwiched between two numbers, we write the interval like this. It's making one combined statement about x. This statement says that 1 is less than x, which is less than or equal to 5. Any number to the left of 1 does not satisfy it, and any number to the right of 5 does not satisfy it. However, any number in between 1 and 5 is included. Since the circle is open at 1 and the circle at 5 is closed, we write the less than and then less than or equal to the way we've done it. Whenever we have an interval on a number line shaded between two values, you can write it the way we did and then add an equal sign to one or both of them. So that's a repetition of what I said earlier in when I was using my own handwriting. And so our answer for this, finally, long explanation, our answer for this is the answer that you see right there. Okay. Here, we'll make it a little bit quicker now. You have 3 different intervals in this question, so you want to have 3 different statements about x separated by commas. Remember, this one on the right goes infinitely far. That arrow goes infinitely. Sometimes people make the mistake of thinking it stops at 7 because the arrow does. But when you see an arrow like that in that context, it means you're shading in the number line infinitely long. So the first interval there is -6 less than or equal to x less than -3. The second interval is 1 less than or equal to x less than or equal to 3. The third interval is x greater than or equal to 5. So we want to state that we're talking about real numbers, and so we put them all together with commas in between in the appropriate set notation, like you see at the bottom of your screen. Now, sometimes we also want to use interval notation. When we use interval notation, it's implied we're dealing with real numbers. In interval notation, a round bracket means we're not including that value. A square bracket means we are including that value. So for example, if I'm in interval notation and I write 2, 3 like that, it means we're talking about every number between 2 and 3, but not including 2 or 3. That would be 2 less than x less than 3. On the other hand, if I write 2, 3 like that with a square bracket, that would mean we're including the 2 If I wrote 2, 3 like that, it would mean that we were not including the 2, but we were including the 3 because the 3 had the square bracket. And if both the 2 and the 3 have the square bracket, that means we're saying 2 is less than or equal to x is less than or equal to 3. Now, sometimes we're talking about an interval where we're including all numbers to the left of a number or all numbers to the right of a number. In those cases, imagine this first one here. Imagine we were looking at that interval. What we have is the number 2. This is shaded in, and we're talking about all numbers to the left infinitely long. So what you might be saying is, well, there's no starting number for this interval. Over here, what could you possibly write to indicate you're starting the interval? And the answer is, to the far left, you can put a negative infinity. So you could say in interval notation that this interval would be negative infinity to the far left, positive 2 to the far right, with a square bracket. And if we had something like x greater than 5, like this second one, then what we could do is think of 5 here, color in all the numbers to the right of 5, infinitely long. We might think to ourselves, well, there's no number on the right-hand side that's helping me close that off. But then we'd say, well, let's consider it to be infinity. And if we do that, then we'd be saying we're including all the numbers between 5 and infinity. You cannot include infinity, so you put a round bracket, and we're not including the 5 because there's an open circle there, because in the example I'm using, it just says greater, so we put a round bracket there. So if we're thinking of a number to the far left, it's negative infinity. If we're thinking of a number to the far right, it's positive infinity, even though those technically aren't numbers. And in any case where we have an infinity or a negative infinity, we use a round bracket on those. So let's go back and answer the previous questions using interval notation. The first question was this one. We've got negative infinity on the far left. We've got positive infinity on the far right. This arrow indicates that we're going infinitely long. So we can say x is a number somewhere in between negative 2 and positive infinity. We're including the negative 2, so we put a square bracket. We're not including infinity because infinity or negative infinity always gets a round bracket, and that's our answer. X is an element of the real number interval that includes all the numbers between negative 2 and infinity, including negative 2, but obviously not including infinity. Okay. Now, sometimes people will say, oh, okay, so we included all the numbers between infinity and negative 2. That would be incorrect, though, because in this course, in this context, we're always reading left to right. We always read it that way, so give the smaller, then the bigger. Okay? So in this question here, this arrow means we're going infinitely to the left, so we can shade that in, at least in our mind's eye. We can say we've got negative infinity on the far left, we got positive infinity on the far right. We're including all the numbers between the negative infinity and the negative 1. We're not including the negative 1 because it's open circle. We're not including the negative infinity because it's infinity, and that is our interval notation. Okay. For this one here, we have two different intervals. So we're going to have two different intervals in interval notation. The first one will be between negative infinity and negative 3, square bracket on the negative 3, round bracket on the negative infinity. The second interval is between 4 and positive infinity, round brackets on both. There's always a round bracket on infinity, and this has an open circle. So we want to indicate that we could be, x could be a number in either one of these intervals. The way we do that is we put a u there, And what we're saying is x is an element of the union between those two intervals. We're uniting them, so to speak. Okay. Here, this is actually a pretty easy one. It's a tougher one with set notation, perhaps, but with interval notation, this tends to be one that students find pretty easy. We want to include all the numbers between 1 and 5, round bracket on the 1 because it's an empty circle, closed bracket on the 5 because it's a closed circle. So we want to say x is an element of that interval. And then finally, we want to put these three together. So we're going to say x could be anywhere between -6 and -3, square bracket, round bracket, in union with 1 to 3, couple of square brackets, in union with 5 to infinity, square bracket, round bracket. Okay.